Bismillahirrahmanirrahim. So we stopped here, we talked about the three different ways to avoid collision for the Cmpe457-2018-04-16. We talked about IFS, interframe spacing, as one way of avoiding the collision. And then we talked about the contention window. And we said that each node will independently calculate a random number within that window. And based on that, it will calculate the slot or the end of the time that it has to wait before it starts to send. And even during that time, every time slot, it has to sense again. And if it finds that the channel is busy, then it stops the timer and then resumes the timer in the next transaction or then in the next transmission. So this will give the node the more priority next time because it has to wait for a shorter time. The third way is the acknowledgement. Actually, there is a fourth way which is not included here because it's optional in the as part of the standard. So we said that interframe spacing can also be used for defining priority. And we said that if the station finds the channel busy, then it doesn't actually restart the timer. Instead, it actually suspends the timer so that in the next transmission, it will resume the timer from where it stopped. So this way, the node will not start from scratch every time. So in the next time, it will have more priority. Based on that, this is the flow chart. As we have discussed before for the Cmpe457-CD, because we can detect the collision, we didn't have to do all these ways or all these methods to avoid the collision. We didn't have to do that. Therefore, the collision avoidance was actually part of this branch, was part of here. Okay? So after you detect the collision, then you want to avoid having collision again. So this way, the collision avoidance part was here. But in fact, because we cannot detect the collision, but we just can try to avoid it. So this method has been moved here with some modifications. The first modification, of course, is that similarly, of course, we have to calculate a random time to wait within the window, and this window is similar to Cmpe457-CD. It's 2 to the power k minus 1, so we generate any random number between 0 and 2 to the power k minus 1. That's similar. However, the difference here is that during the wait time, we have to sense the channel every time slot. So this is what's written here. And if we find the channel busy, then we suspend the timer, and then we stop in the next time. We come here, we resume the timer. Okay? So this is one difference that in Cmpe457-CA we had to do. Of course, because we have to do this collision avoidance in the main branch of the logic, we didn't have to do that here. Because we have to always do this even before the collision happens to try to avoid it. So this is a major difference here that we can notice for the case of Cmpe457-CA. Other than that, you send a frame and you wait for the acknowledgement, similar to Cmpe457-CD. And of course, before that, we have to wait for IFS. So those two are the major changes we have in Cmpe457-CA flowchart. Okay, so the second category is the controlled access. As we have discussed in the beginning, controlled access tries to eliminate collision completely. So in controlled access techniques, there is no collision. But in that case, because it's controlled, we need to have a designated node that actually controls that access. Okay? So it's like we are in a meeting and we have a moderator. So this moderator will organize how the channel will be accessed. Okay? And the third category, as we said before, and the third category for channelization, we prefix the channel assignment, in which case there is no need for the moderator. It's like we come to the meeting and we know that we have to take turns in a certain order. Okay? So we know that we set these rules in the beginning, in which case, okay, so we all will abide by these rules, then we don't need a moderator, assuming that everyone will abide by the rules. Okay? The good thing about the controlled access is that if you have a moderator, then you can change the access strategy at any point in time because you have one controller. So this controller will have the control to change the access strategy at any point in time. Okay, so this is the main difference. There are 3 different methods here, although we'll talk about only 2. The third one is token passing, which we talked about in 455. And because it's obsolete, we did not include it here, although it's in the textbook, but we did not include it here. So here we have 2 methods or 2 techniques that we will talk about. The reservation, okay, and of course for channelization we have reservation as well. But the difference is that for channelization the reservation is fixed, in which case we don't need a controller. But here we talk about dynamic reservation. So the reservation can change from a certain point in time to another, as we will see. And the polling, which we will talk about. So for reservation access methods, what happens is that we first have many slots. These many slots are, we call it reservation slots. The number of these reservation slots equal to the number of nodes in the network. So for example, we have 4 nodes, or here, like we have 5 nodes, let's say. Here we have 5 nodes. So in that case, we need to have 5 different many slots. Okay? Each one will be assigned one of these many slots. Okay? Someone might say, okay, so what is the difference between this and CDMA? Remember, these many slots are not for sending data. This is just for declaring the fact that you have something to send. So in this many slot, you only need to send an indicator that you have something to send. That's why we call it many slot. It's very short. And it's negligible in the time frame, it's negligible. But the frames will say, I have something to send in its own allocated many slot. Okay? So here, like for example here in this case, we have 1, 2, 3, 4, 5. So in that case, node 1, node 3, and node 5, both these 3, they have something to send. In which case, they will send in their many slots just indicator, just one, to say that I have something to send. In which case, in the data part, only these 3 stations will send. So station 1, and then station 3, and then station 4 will send. And then we have the reservation many slots again. And then each node will have to declare whether it has something to send or not. And in this next phase, only node 1 has something to send, in which case it will send. And then later on, there is no reservation, which means that the channel is totally idle, waiting for someone to send. So that's how we... So here, why do you think we need a controller? We didn't mention anything about the controller here. صح? We didn't talk about anyone to control this access. So we can do that without a controller. Can we? Can we do that? Can we do that without a controller? Remember, each node doesn't have any global picture. So when node 3 tries to reserve, it doesn't know that node 1 and node 5 or node 4, they have something to send as well. So implicitly here, what will happen at this point, which is not mentioned in the textbook, actually it's missing in the textbook, the controller will send here a declaration to all nodes that node 1 will send first, then node 3, then node 4. And nothing else. So node 3 knows that its time slot is after node 1. Okay? And then node 4 will know it's after node 3, and no one else needs to send. So because here we have only 3 data transmissions. In the next frame we may have 1. So who will control that in this In this phase of transmission, we have 3. In this phase of transmission, we have 2. In this phase of transmission, we have 1. Who will control that? The controller. So here, even though it's not explicit, but we need to have a controller. So in the reservation method, we do need to have a controller to control who will send in the data transmission phase, whether it's 1 node, 2 nodes, 3 nodes, 5 nodes, because the number of stations here is dynamic, is variable. As long as it's variable, someone needs to dictate that, someone needs to control that. So that's why we need a controller in this case. Okay, so this is the reservation method. Here, the overhead is in the many slots only. Okay, and the many slots, as we said, it's negligible in the time horizon. It's negligible. So this is the only overhead in this case. Okay, and of course it happens for every one transmission phase. So for one transmission phase, you have n different many slots, and the many slots is like 1 bit, one byte. It's very small for the entire transmission phase. But the second method is polling. And in the polling, we do have a primary. Now the controller is actually explicit. We call it a primary node. Every other node is called a secondary node. Okay? And there are 2 scenarios here. The transmission is totally controlled by the primary node, either in the downstream or in the upstream, which means that here we are talking about downstream transmission. Here we talk about upstream. يعني ايه downstream and upstream? Downstream meaning that the primary node needs to send data to one of the secondary nodes. In this case, we use the select function. Okay? So the channel is always controlled by the primary node, either in the downstream or in the upstream. So in the downstream, if the primary node wants to send data to one of the secondary nodes, then it sends a select function or a select signal to indicate that I want to send to node B in that case. Then node B has to acknowledge the fact that it's able to receive something. And then the primary node will send the data, and then node B will acknowledge. So remember that everything is always initiated by the primary node. So there should be no collision whatsoever, right? Because always everything is initiated by the primary node. So we are in a meeting, but we are all silent until the moderator or the primary person in the meeting would say, "Hey, you, I want to speak to you," and then he starts to speak to a single person in the meeting. طيب. In the upstream, what happens is that we use the polling, which means that, again, the primary node is the one that polls people. And again, because we have a controller, this polling order may change. I'm allowed as a main controller or the primary node in this system, I can change the polling order. I have full control. Okay? Changing the polling order might actually introduce some kind of a priority so I can change the order to give priority to certain people. I can do that. Okay? So the way it works is that when I pull up, I always pull nodes in a certain order. Do you have something to send? Do you have something to send? Do you have something to send? If the node has nothing to send, then it sends a negative acknowledgement, which means that negative, I have nothing to send. Okay? If the node has something to send, then it starts sending right away. It doesn't need to say, yes, I have something to send, and then it sends. Those are merged, and then you send the data directly. And then the acknowledgement will indicate that, okay, I received it. Okay? طيب. In terms of overhead, okay, the calculation of the overhead in the two cases is slightly different. I would say in the polling access method, the overhead is slightly more because everything is initiated by the primary node, and the primary node needs to always either select or pull. So you always dependent on the primary node to initiate the communication all the time. If you observe, every single transmission requires either select acknowledgement and then acknowledgement again, or pull and then acknowledgement. Every single transmission. Okay? So it's not for the entire transmission phase. It has to be done for every single data transmission. Okay? So the overhead here should be slightly more. And in fact, in the exercises, we will calculate this. We will quantify the amount of overhead in the polling access mechanism. So any question here? So this is the downstream and this is the upstream. For channelization, as I said, we don't need any controller. But the consequences of not having a controller is the fact that we have to fix everything. So we have to fix the reservation. Okay? Then and only then we can get rid of the controller. But let's see the consequences of this. So in channelization, what we do is that we divide the channel resources either in the frequency domain, or in the time domain, or in the code domain. And we'll talk about what this code means. Okay? So we know that if multiple nodes send at different frequencies, they will never have any collision. So we know that. So we can use this to provide multi-access mechanism using FDMA. So in each case, we need to talk about the pros and cons. Simply, for FDMA, we divide the whole spectrum into different channels or different frequencies. So we prefix certain node to send at certain frequency channel. That's it. So we prefix that, and it goes on like this all the time. So node 1 always send in channel 1. Node 2 always send in channel 2. Node 3 will send in channel 3, and node 4 will send in channel 4. In which case, the composite signal will be like this in the frequency domain. And then, if any node needs to receive from node 1, it needs to apply a filter on channel 1 to receive any transmission from node 1. That's it. Okay? So this is easy. So the advantage of FDMA is that it's simple. We know how to do that. The problem or the disadvantage, we have two disadvantages here. One is the fact that in frequency, filters are not perfect, right? So in which case we need to have certain guard bands between these channels. We need to have some guard bands. We call them guard bands. So this will allow the transmission from the nodes not to overlap. Because if you, there's no perfect filter. The filter is always, there's no filter like this. There's nothing like this. It's always like this. So if you have two channels, then you need to have like some, then there is some overlap, which means that there is some interference. So to minimize this interference, you actually have to separate the frequency channels from each other, in which case you need to apply some gaps, some guard bands between them. So that's one problem. What is the other problem? Well, the other problem is that node 3, as you can notice here, node 3 is silent. What happens to the frequency channel allocated to it? It's wasted, yes. So it's wasted. This is the consequence of having no controller, right? Because if you, in the reservation, we can avoid this simply, right? Because node 3 will not make the reservation, in which case the controller will say, okay, I don't have to waste this time. Okay, but this is the job of the controller. So because here we have this reservation prefixed, we cannot do that. We cannot do any dynamic reservation. It's always fixed, and in which case we can run into some scenarios where we can waste the frequency. طيب, here the available bandwidth of the common channel is divided into bands, so that's the main idea of the FDMA. TDMA is similar, but instead of dividing the channel or dividing the frequency, we divide the time. طيب, so what is the problem here? Again, if you have a time slot that's assigned to a node and the node has nothing to send, like here node 3, again this time slot is wasted. What is the other problem here? Similar برضو to the case of FDMA in a way. We should have a gap. Well, here the gap accounts for the propagation delay because the nodes are geographically separated, right? So each node wants to send to another node. It has to go through some propagation delay. So the propagation delay between the nodes is slightly different, right? So in order to make sure that in your time slot, when you send data, it propagates, it has to propagate, has to take time, even like 1 nanosecond or 2 nanoseconds. So to make sure that during the propagation no other node will send, again we need to put some guard bands. Here the guard bands are in the time domain, not in the frequency domain. In the frequency domain we didn't have to do that. We don't care about propagation, right? Because we always send in a different frequency. So as long as we have guard bands in the frequency domain, we don't have to worry about propagation, right? We didn't have to do any synchronization issues. The problem also here is that, well, whenever you have distributed nodes that need to agree on a certain time instances, then you have the problem of synchronization, right? Because the nodes need to calculate where is the beginning and the end of its time slots, right? And it calculates that based on its own clock, which is always has some clock drift compared to all the other nodes, right? So there is always a synchronization issue in the TDMA, and of course they have some solutions for this, but the solution adds more overhead. So remember we talked about self-synchronization in the line coding schemes, right? So they send some bits in the beginning to allow for synchronizing all the nodes. Okay, so we always have a synchronization issue whenever we have distributed nodes abiding by or trying to follow a certain time slot. Okay, so synchronization issues in the TDMA is always a challenge. Any questions so far? Okay, so so that's TDMA. The third one, I'm not sure if any of you is familiar with CDMA. Any of you is familiar with CDMA? Okay, so CDMA is kind of, by the way, all the 3G standards are based on CDMA. So here, one channel carries all the transmissions simultaneously. So all the nodes send on the same frequency at the same time without any collision, which is kind of interesting, right? So how does this happen? Well, the best way from real life to understand how CDMA works is that, well, if we are in a meeting and we have two people are talking and two other people are talking and they are interfering with each other, right? So if they are talking, all the other people in the meeting would not be able to understand anything because it's like they are talking simultaneously. So to you, this will sound like a noise. You will not be able to listen to any of these speeches, right? But if we assume that two people are talking in English and two other people are talking in Chinese, and the reason for these two languages are, we call them orthogonal to each other. There's no similarity whatsoever. Okay? The two languages are so different. Okay? So other people, if you imagine, other people can, in fact, listen. People who understand Chinese will be able to listen to the speech in Chinese, and people who are, understanding English, they will be able to listen to the English language, even though they are happening at the same time in the same room. Okay. So this is basically how CDMA works. What we try to do is that we take the data, we take the actual digital data, zeros and ones, and then we put them in orthogonal domains. We try to do some separation between them. Okay? And then we allow them to go at the same time. At the same time, at the same frequency. And then people who understand certain code or certain language will be able to listen to this language from the composite signal. Okay? So this is a real live explanation for how CDMA works. So let's go into the mathematical part of it. Basically, what we do is that we take the data from each node and then we multiply it by a code. This code will just code this data in a language which is totally different from all other languages. Okay? So node 1 will have code 1, which will be multiplied by the data to kind of shift this data in an orthogonal domain for node 1 transmission. Node 2 will have code 2, and node 3 will have code 3, and node 4 will have code 4. Okay? Okay, so as we can imagine, these codes have certain properties. These codes are designed to fulfill two major and fundamental conditions. One, multiplying any code I with itself, okay, will always result in n, such that n is the number of nodes. Which means that a code is highly correlated with itself. And multiplying code I with code j such that I not equal to j is always a 0. Which means that these codes are orthogonal to each other. They have absolutely no correlation, which is what we have explained as you have two different languages which have no similarities whatsoever. Okay? So, what is the implication of this? Well, if we imagine that all these nodes send with these different codes, what we will have on the channel at the end is data 1 multiplied by code 1, data 2 multiplied by code 2, data 3 multiplied by code 3, and data 4 multiplied by code 4. Right? So this is the composite signal, and we'll see how this looks like. Okay, so now a node wants to receive data 2, for example. Okay? This node, all it needs to have is code 2. So if I want to receive data 2, the receiver must have code 2. So what is the implication of this? So if I want to receive data 2, all I need to do at the receiver, I need to multiply this composite signal by code 2. Okay? So what is the result? So code 2 will be multiplied by D1, C1, C2, right? Okay, what is the result of this? What is the result of C2 multiplied by D1, C1? 0. And then D2, C2, C2. D2 multiplied by A, by N. And then D3, C3, C2. What is the result of this? 0. And D4, C4, C2. What is the result of this? Always 0, right? So I will end up with D2 multiplied by N, which means that only the data 2 will be actually amplified. Okay? Will be amplified. Why? Because the code is highly correlated with itself. And it's totally uncorrelated with all the other codes. So these properties are very, very important for these codes for CDMA to work. So, okay, so how does it look like for using بقى numbers يعني? So these are the codes, and we'll see how can we generate these codes. It's very easy. Okay, so these codes, they work. We have 4 codes for 4 different nodes. So if we have a network of 4 nodes, then we need to have 4 codes, right? Very simple. And these codes, if you try to, actually these codes, because they are always composed of 1 and minus 1, as you can notice here, there's no 0. Why? Because if you multiply C1 by itself, okay, so 1 times 1, plus 1 times 1, plus 1 times 1, plus 1 times 1. So what is the result? N. If you do the same for C2, N, right? If you do the same for C3, N. C4, N. Okay? Multiply by A, C1 times C2. 0. The multiplication is very easy. 1 times 1. Plus 1 times minus 1. Yani you take each item and you multiply it by the item corresponding to it in the other code. It's very simple. They call it dot product. Okay? So if you multiply these codes, any 2 codes, the answer is always 0. Except if you multiply the code by itself, the answer will be always a N. That's why we don't need to have zeros here. Why? Because if you have zeros, the multiplication between the codes will still be orthogonal, but the first property will not be fulfilled. Why? Because 0 times 0 is 0, right? But minus 1 times minus 1 is 1. So if you have 0 in any of these codes, multiplying the code with itself will not result in n. Will result in a number which is less than n. Because we need to have this correlation very high. That's why we actually have to change the 0 to minus 1. So that we can raise the correlation. The correlation of the codes with itself needs to be very high. Okay? So these are codes which fulfill the 2 properties we talked about. Multiplying any code by itself will result to n. Multiplying any 2 codes will result to 0. Yes. Yes. Also, we'll talk about how can we generate this. There's always a mechanism how to generate these codes. They have to be in multiples of 2, which means that again, we have this 2 to the power n. So it's either 2 or 4 or 8. We don't have like 5. Even if you have 5 nodes, you have to have 8 codes. And we'll talk about why. So the first thing we do is that we have to convert any data bit of 0, we have to convert it into a minus 1. Right? Why? Again, to have high correlation in the case when we multiply the code by itself. Okay? So minus 1 times minus 1 is 1. But 0 times 0 is 0. So we need to have a high correlation. And 1, data 1 will remain as 1, positive 1. And then if you are silent, if you are in silence mode, you don't want to send any data, you can send 0 in that case. Okay, which means that the data that you will send, 0 multiplied by any code is always 0. So it's like you are not affecting the summation. Okay? So your contribution to the composite signal will always be 0. So there's no effect. Okay? طيب. So if node 1 wants to send 0, then we convert 0 to -1. So this is the data that we will send. Right? So node 1 wants to send 0. So we convert 0 to -1. And then we multiply -1 times the code, which means that it's -1, -1, -1, -1. Right? Node 2, same thing, wants to send bit 0. Then again, we multiply -1 times the code. Here the code is different, of course, and this is the multiplication. And node 3 happens to be silent. It doesn't want to send anything, which means that the result will always be 0, so it doesn't contribute anything to the composite signal. And node 4 wants to send 1 in that case, so 1 multiplied by the code will be the exact same code, in which case the summation of all of these will be here we have -1, and here we have -1, so -2, and here we have 1, so the result is -1. So the composite signal is simply the summation of all these signals together. So this is the composite signal that will end up being on the channel. Okay? So that's how it works. Simple, or any confusion here? So if you are silent, you send 0, which means that you don't contribute anything to the composite signal. If you want to send 0, then we multiply -1 by the code. If you want to send 1, then you multiply the 1 by your code. Okay? So signal-wise, so the same example we had, we put it in a signal way. So we have node 1 wants to send bit 0, which means that we multiply -1 by the code, so the result is -1. So in terms of signal, the signal will be -1, -1, -1, -1. So when we get the summation of all of this, so here we have -1, 1, and then 1, so the result will be 1. And here we have -3, and here we have -1 and -1. So this is the composite signal that will end up being on the common channel. And remember, here we're sending at the same time, at the same frequency. So we get the composite signal. Okay? Type. The end wants to send a bit 0, which means -4, node 2, which is 1, -1, 1, -1. Same thing because this composite signal, if we do the same, if this composite signal was in the without the codes, then this composite signal will have no orthogonal domains that will allow us to extract any of the data that we try to send from this composite signal. But now, imagine if, so we have here, so the data on the channel is this. Imagine if if we want to receive node 2. Remember, node 2, right? So in that case, we will use the code. So this is the code, right? So we multiply the code, which is 1 -1, 1 -1, times the composite signal. Multiplication is easy. We'll multiply, this is 1 and this is -1, so the result is -1. This is -1 and this is -1, so the result is +1, sorry. This is -3 times +1, so the result is -3. Right? And this is 1, this is -1, so the result is -1. So the multiplication is like item by item, very easy. So what happens now is that at the receiver, what we will do is that we will apply a summation of all the result. Okay, so we actually sum 1, -1, sorry, +1, and then -3, and then -1. So the result is -4. Remember, -4 is actually -1 multiplied by 4, and 4 is n. So -4 is in fact -1 times n. Okay, which is what we have proved symbolically before, right? So we do that using what they call an integrator. So the integrator is nothing but it sums these numbers one by one. So here I have -1, so I go -1. And then I have 1, so I go like this. So the result is now is 0. And then -3, so I go -3. And then -1, so I go -4. So in fact, at the receiver, we apply an integrator. Integrator sums everything, right? So here, -4 is in fact -1 times n. So if I divide by n, I get -1. And -1 is 8. We know that -1 is 8, is 0, right? That's how we do it. So the way that we generate these codes is very simple. It has to be multiples of 2, which means that if I have 4 nodes, I need 4 codes. If I have 5 nodes, then I have 8. So I have to generate 8 codes. Use the first 5. Use the first 5 for the 5 nodes, but the other 3 will have to always be generated. Yeah. So we generate these codes through what we call a Walsh table. And the Walsh table is very easy to generate. It's a recursive table. Recursive معناها إيه? Recursive معناها we always have the second table is always the Walsh table from the previous step repeated 3 times, but then the 4th one is complemented, which means that it's multiplied by -1. So we start from W1, which is, say, +1. You can start from -1, by the way. It doesn't matter. So you can have Walsh 1 as 1 or -1. Doesn't matter. Okay? So in that case, you have Walsh 2, which is double the dimension, will be to repeat this Walsh 1 3 times, and the 4th one is complemented or toggled, right? Which means that you multiply by -1. So if you notice, Walsh 4 is the exact same Walsh 2 repeated 3 times, and the 4th one you multiply by -1. Walsh 8 will be to take this table. This table you will repeat it 4 times, such that the 3 times in this triangle will be the same, and the 4th one will be multiplied by -1, and so on. Okay? So this method will always guarantee the fact that if you try any code, you multiply by itself, the answer will always be n. And if you multiply any of these rows, try to multiply any of these rows in the table, the answer will always be 0. Okay? Which means that Walsh table codes, or sometimes we call them chips, okay? These chips or codes will always fulfill the 2 properties that we talked about. Correlation of the code with itself is high, correlation of the code with any other code is 0. Okay? Any question? All right, so because of this fact, okay? Because we always generate the Walsh table of double the dimension, right? So n has to be multiples of 2, which means that if you have 2 stations, then you need to generate Walsh 2. If you have 4 stations, then you need to generate Walsh 4. But if you have, for example, 90 stations, okay, so m is it cannot be 6, because 2 to the power 6 is 64, right? So 64 will not be enough for 90 stations. So it has to be 7. And 7 will give you 128 codes. So you have to generate a Walsh table, Walsh of 128. Okay? But then I have 90 stations. That's fine. Take any 90 rows of this 128, okay, and assign them to the stations. And consider the remaining codes to be ready for future expansion. If the number of nodes increase, then you have other codes to assign to these stations. Okay, so from 90 all the way to 128, you don't need to regenerate the Walsh table again. If the number of nodes increase beyond 128, then you have to go with a m equal to 8, in which case you have to generate a Walsh code of 256. Okay, so the Walsh has to always be multiples of 2 because of this. So that's how CDMA works. So this is the proof that we have done. This is the proof that we have done at the beginning. We said that this is the composite signal, right, which is D1 multiplied by code 1, D2 multiplied by code 2, and so on. So if we need to receive the data from station 1, then we multiply by C1, which means we multiply D1, the composite signal by C1, which means that multiply each of these items with C1. So D1, C1, C1, this will be D1 multiplied by N, and then D2 multiplied by C2 multiplied by C1 is always 0, C3 multiplied by C1 is always 0, C4 multiplied by C1 is always 0, so you will end up with D1 multiplied by N. Okay, so easy, straightforward. Okay, so that's so that's how CDMA works. Of course, there are some details. It's not as easy as it looks, because there are, in practice, it's not ideal like this. In practice, there are some other issues we have to take into consideration. For example, when we say it's D1 multiplied by C1 and D2 multiplied by C2, remember that at the end on the channel we send signals, right? And these signals, especially if you're talking about wireless, these signals they go through attenuation, right? So in fact, if you are sending D1 and D1 is 1, what you will receive on the channel on the other end is not actually 1. It's actually 1 minus something. It's attenuated and it's actually distorted and so on. So we have to do some amplification to the signal, and we have to do some estimation in order to make sure that that any attenuation will not affect the signal. And also, when we take that, when we talk about the fact that if we want to generate or if we want to receive the data from station 1, we use code 1. But actually, when we talk about in real life, these codes are, again, these chips are continuous, and in real time, these codes have to be generated at all the stations. So again, there has to be almost perfect synchronization between generating the codes on either stations, in which case, again, there is some synchronization issue for CDMA, which is one of the disadvantages of CDMA. So synchronization is an issue, attenuation of the signal is an issue, and in that case, we have to account for this when we design a real CDMA transmitter and the receiver. And that's why, because of these issues, the transceiver using CDMA is complicated. It's not easy, and in fact, it's more complex compared to TDMA and FDMA. But of course, the advantage or the benefit overweighs the complexity of the receiver, because of the fact that we can send from multiple stations at the same frequency at the same time. This is in fact a huge benefit, which in cellular systems, for example, you don't have to have any frequency allocation, so you just allow the signals or allow the stations to send at the same time, at the same frequency, and you don't have to have any frequency planning or something like this. So, so the benefits of CDMA overweighs the complexity of the transceiver, and that's why it was very, very, very attractive for 3G transmission until recently. For 4G, they started to have a totally different technology, which is, although it's based on FDMA, but it's highly more complex. They call it OFDMA. So 4G is based on OFDMA, which is totally different from CDMA. But with this OFDMA, the transmission throughput is much, much higher compared to CDMA. And that's why we have in 4G transmission or in 4G cellular systems, the data transmission can get as high as almost, it touches like 1 gigabits per second, which is very close to the wired network, which is quite impressive. But anyway, so these are, of course, here we're just superficially talking about how CDMA works in terms of theoretical concept, but the design in real life is much more complex. So any questions? Okay, so we'll probably